Okay, now we are going to discuss the correspondence to the sample sum. So in this lesson, the previous theorems and properties that we show was about the sample mean, but there is an equivalent approximation for the sample sum. So suppose we have the same setup, x1 until xn are IID random variables with common mean mu and common variance sigma square. And the notation that we are going to use for the sample sum is going to be Sn is the sum of x1 and x2 and so on until xn. Okay, now if we want to write the sample sum as a function of the sample mean, so remember that the sample mean is going to be the sum of the n random variables x1 until xn over n. So that means that in the numerator part, this is going to be Sn over n. So that means the sample sum is n times the sample mean. Okay. We had a result about a linear transformation of a normal random variable. We can use it to find the approximate distribution of the sample sum when n is large. So remember the property. I'm going to put it here. The property says that if we have a random variable y that is distributed normal with mean expected value of y and the variance of y, then the distribution of a times y plus b is going to be normal with the mean is going to be a times the expected value of y plus b, but the variance is going to be a squared, the variance of y. Okay, we discussed that property. And now we can use it to find the distribution of the sample sum. So we have that Sn, the sample mean, is normally distributed with mean mu, and the variance is sigma squared over n, right? That is the central limit theorem. So using that, we have that n times Sn is going to be the sample sum Sn. And using this property here, we have that this distribution is approximately normal with mean equal to n times mu, and the variance is going to be n squared because it's n times Sn, and we have that a times y, the variance is a squared times the variance of y. So in this case it's n squared times the variance of the sample mean, that is sigma squared over n. So this variance should be equal to n times sigma squared. Okay, so the definition that we have is that under the same setup, we have that for large sample size and the sample sum is normally distributed with mean n times mu, where mu is the expected value of the random variables, and the variance is n times sigma squared. This sigma squared is the variance of the random variables. Okay, let's see this example. Suppose the distribution of weights of strawberries in ounces is described by the following distribution. Okay, suppose that for edges between 0 and 2. Suppose you are trying to make a pie that calls for 1.5 pounds, that is 24 ounces, of strawberries. What is the approximate probability that 30 strawberries will be enough? Okay, we need to calculate we know that x is the weight, right? So we need to calculate that the sum of the weights of 30 strawberries is enough. So we have that S30, the sum of the weights of the 30 strawberries, is greater or equal than 24, right? Okay. By CLT, we have that S30 is normally distributed with mean equal to n times the expected value of x, and the variance is n times the variance of x, where x is the random variable here. N in this case is equal to 30, right? We have that. So we just need to calculate the expected value and the variance to know the distribution of this sample sum random variable. So the expected value of x, in this case, we have this distribution, this PDF. So the expected value is the integral of x times the PDF, that is 1 minus x over 2 over 0 and 2, right? If we calculate that, this is about 230. Now we just need the variance. The variance, we can use this rule, that is the expected value of x squared minus the square of the expected value. And this is the integral from 0 to 2 of x squared times 1 minus x over 2 dx minus the expected value of x, 2 over 3 squared. And if we calculate that, this is 2 over 9. So finally, we have that S30, the sample sum, is normally distributed with mean equal to n times this expected value. So it's 30 times 2 over 3. This is 20. And the variance is going to be 30. It's n times the variance of x. So it's 30 times 2 over 9. That is 20 over 3, right? So if the variance is 20 over 3, the standard deviation should be approximately, well, is the square root of 20 over 3. That is approximately 2.582. So finally, we have already the distribution of S30 that is normal. So we can calculate this S30 greater or equal than 24, because it's the probability that we need to calculate. And we can calculate that using the applet, because mu is equal to 20 in this case, and we can use sigma to be 2.582, and the upper tail in this case is x equal to 24. This is what we want to calculate here, and if we do that, it's 0.0607.